Hi everyone, my name is Jenna Reddy and I'm a CSC data science student at IRA Hyderabad. In this video, the topic is ETHERFEST theorem. ETHERFEST theorem using IH sigma t is equals to H sigma t and hence IH and DD t sigma t is equals to sigma t H and writing ohms equals to sigma t or divide union ohms on union sigma t. We have ETHERFEST theorem. The second theorem term disappears in sigma. Sorry, ohms is a time-independent operator like momentum spin. Note we are distinguishing between intrinsic time dependence of an operator and the time dependence of its expectation value in a given state. This is very reminiscent of a result which follows from Hamilton's equations in classical mechanics for a function of position, momentum, and possibly time explicitly. That is, ohm of pxt d dt ohm of pxt equals to d ohm dx dt plus derivative of sigma derivative of ohms derivative of p dp dt plus derivative of ohms derivative of t equals to derivative of ohms derivative of x derivative of h derivative of p minus derivative of ohms derivative of p derivative of h derivative of x plus derivative of ohms derivative of t equals to ohms comma h plus derivative of ohms derivative into derivative of t, where the notation ohms h is called the Poisson bracket of ohms and h and is simply defined in terms of the expression on the line above, which is replaced. For ohm equals to x on ohm equals to p, we can in fact recover Hamilton's equations for p and x from this more general expression. In fact, for h equals to p square 2m plus v of x, we can further show that d dt of x equals to p power m and d dt equals to p equals to minus dv of x into dx, which looks very close to Newton's law. Note though that dv of x divided by dx is not equals to dvx divided by d of x is general. In general, this correspondence is not just a coincidence in the sense that Heisenberg was influenced by it in coming up with this formulation of quantum mechanics. It confirms that it is expectation value of an operator rather than the operator itself, which is close to the classical concept of the time evolution of some quantity as a particle moves along a trajectory. Similarly, of formalism is not the same as identity of concepts. Etherfest theorem does not say that the expectation value of a quantity follows a classical trajectory in general, which is what is does ensure is that if the uncertainty in the quantity is sufficiently small, in other words, if delta x and delta p are both small in relative terms, then the quantum motion will approximate the classical path. Of course, because of this uncertainty principle, if delta x is small, then delta p is large. And it can be more only be relatively small if p itself is really large. That is, if the particle's mass is macroscopic. More specifically, we can say that we will be in the classical regime if the de Broglie wavelength is much less than the experimental uncertainty in X. In the Stern-Gerlach experiment, the atoms are heavy enough that for a given component of the magnetic moment, they follow approximately classical trajectories through, through the inhomogeneous magnetic field. Introduction and motivation. Folklore alleges, and in the some texts it states explicitly, if as will emerge not quite correctly asserted, that quantum mechanical expectation values obey Newton's second law. The pretty point here at issue was first marked by Paul Ehrenfest in a paper scarcely more than 2 pages long, one concerning the substance and impact of that little gem. Max Jammer at P 363 is in his the conceptual development of the quantum mechanics has to say that for the harmonic oscillator wave mechanics agrees with ordinary mechanics had already been shown by Schrödinger too. A more general and direct line of connection between quantum mechanics and Newtonian mechanics was established in 1927 by Ehrenfest, who showed by a short elementary calculation without approximations that the expectation value of the time derivative of the momentum is equal to the expectation value of the negative gradient of the potential energy function. Ehrenfest's affirmation of Newton's second law in the sense of averages taken over the wave packet had a great appeal to many physicists and did much to further the acceptance of the theory, for it made it possible to describe the particle by a localized wave pocket, which, though eventually spreading out in space, follows the trajectory of the classical motion, as emphasized in a different context elsewhere. Ehrenfest's theorem. Ehrenfest's theorem is indexed is most quantum texts, though the celebrated authors of some classic monographs have, so far as I have been able to determine and for reasons not clear to me, elected pass over the subject in silence. The authors of the text just cited have been content simply to rehearse Ehrenfest's or original argument and to phrase their interpretive remarks so casually as to risk, or in several cases to invite, misunderstanding. Of more lively interest to me at present are the mathematically or interpretively more searching discussions will be found in Chapter 6 of A. Messiah's Quantum Mechanics and Chapter 15 of L. E. Valentine's Quantum Mechanics. Also of interest will be curious argument introduced by David Bohm in 9.26 of his theory, quantum theory. There Bohm used Ehrenfest theorem backwards to infer the necessary structure of the Schrodinger equation. I am motivated to re-examine Ehrenfest's accomplishment by my hope, not yet ripe enough to call an expectation, that it may be served to illuminate the puzzle which I may praise this way. I look about me in this allegedly I look about me in this allegedly quantum mechanical world and see objects moving classically along well-defined trajectories. How does this come to be so? I have incidentally interest also some mathematical ramifications of Ehrenfest theorem in connection with which I am unable to cite references in the published literature. Some of those come instantly into focus when one looks to the general context within which Ehrenfest's argument is situated. From Ehrenfest's theorem, we came to know that the expectation values of the quantum mechanical observables follow laws of classical mechanics. Here we discuss the classical limit, infinity to zero of Schrodinger equation. Ehrenfest theorem. d by dt of sigma ohm equals to 1 by I h of ohm comma h plus ohm dot. d by dt of p equals to sigma of v of sigma into v of xt derivative of uh, phi dx minus integration of pi into derivative of v of xt into phi dx minus integration of phi into v of xt derivative of phi dx, that equals to minus the integration of phi into derivative of v of xt into the phi dx, that equals to minus derivative v of xt equals to f. So we derived Ehrenfest theorem for an observable q in class. d by dt q equals to I by h of h comma q. Apply the above equation to each of the following special cases. In each case, discuss how to interpret the result. When applicable, compare it to an conservation law, a definition, or a law of motion in classical mechanics. Hint: the following results from Griffith's problem on 3.3 may be useful. A, B, comma C equals to A of B, comma C plus AC, A, comma C into B. F of X, comma P equals to high H and dF by dx. Q equals to 1, Q equals to H, Q equals to X. Compute the commutator using H equals to P square. What can you conclude about H comma X in general? Thank you.